Welcome to this essential guide on understanding memory layout, specifically the stack and heap, for beginners working with Visual Studio and Unity. This video will provide a foundational understanding of how your programs manage data, which is critical for writing efficient and robust applications. We'll explore these concepts in detail, ensuring you grasp the core principles. Efficient memory management is crucial for developing high-performance software, preventing crashes, and optimizing resource usage in your applications. Without a clear understanding of how memory is allocated and deallocated, developers often encounter issues like memory leaks, slow performance, and unexpected program behavior. Mastering these concepts will significantly improve your coding practices and the quality of your software. This video aims to demystify these core concepts, providing a clear, step-by-step explanation of memory layout, the stack, and the heap in both C# within Visual Studio and the Unity game engine. We will break down complex ideas into easily digestible parts, offering practical insights that you can immediately apply to your projects. Our goal is to make memory management accessible and understandable for all beginners. When a program executes, the operating system allocates a dedicated block of memory for it, which is then divided into several distinct regions. This initial allocation is a fundamental step, providing the program with the necessary resources to store its code, data, and execute its operations. Understanding these regions is the first step towards effective memory management. The two primary regions we'll focus on are the stack and the heap, each serving different purposes for storing data. While other regions exist, the stack and heap are where most of your program's dynamic data and execution context reside, making them central to understanding memory behavior. We will explore their unique characteristics and how they interact. The stack is a fast, organized memory region used for temporary data, such as local variables and method call information. Think of it as a highly structured area where data is added and removed in a very predictable order. This efficiency makes the stack ideal for managing the flow of program execution and short-lived data. It operates on a last-in, first-out, or LIFO basis, meaning the last item added is the first one to be removed, and it has a limited size. This strict ordering ensures that memory is managed very efficiently and quickly. However, its limited size means that excessive use or deep recursion can lead to problems. In contrast, the heap is a flexible memory area designed for dynamic data, including objects, classes, and arrays. Unlike the stack, the heap allows for more arbitrary allocation and deallocation of memory, making it suitable for data whose size or lifetime isn't known at compile time. This flexibility comes with its own set of management challenges. Accessing data on the heap is generally slower than on the stack, and its memory management is handled by a garbage collector in languages like C#. The garbage collector automatically identifies and reclaims memory that is no longer in use, preventing memory leaks, but potentially introducing performance overhead if not managed carefully. Let's delve deeper into the distinctions between the stack and the heap, observing how data is handled in each. We will examine specific examples to illustrate when and why data is placed in one region versus the other, highlighting the practical implications for your code. This comparison will solidify your understanding of their roles. Value types, such as integers, floats, booleans, and structs, are stored directly on the stack. When you declare a variable of a value type, the actual data is placed directly in the stack frame of the method where it's declared. This direct storage contributes to their fast access and efficient management. Memory for these types is automatically managed, making allocation and deallocation extremely fast. When a method exits, all the value types declared within it are automatically removed from the stack, requiring no explicit cleanup from the programmer. This automatic process is a key advantage of stack-based memory. However, if the stack exceeds its allocated space, it results in a stack overflow exception, a common error in programming. This typically occurs with excessively deep recursion or when large value types are repeatedly allocated on the stack without proper cleanup. Understanding this limit is crucial for preventing program crashes. Conversely, reference types like class objects, arrays, and strings are stored on the heap. When you create an instance of a reference type, the actual data for that object is allocated on the heap. This allows these objects to persist beyond the scope of the method in which they were created. Memory for heap objects is managed by the garbage collector, which periodically reclaims memory from objects that are no longer referenced. This automated process frees developers from manual memory management, reducing the likelihood of memory leaks and dangling pointers. But it's important to understand its behavior for optimal performance. It's important to understand that a variable on the stack for a reference type only holds a pointer or reference to the actual object's location on the heap. This means the stack variable doesn't contain the object itself, but rather an address that tells the program where to find the object's data on the heap. This distinction is fundamental to how reference types work. In C#, memory management is largely automatic, handled by the Common Language Runtime, or CLR. The CLR provides a managed execution environment that simplifies many aspects of programming, including memory allocation and deallocation. This abstraction allows developers to focus more on application logic rather than low-level memory details. The garbage collector within the CLR automatically reclaims memory from objects that are no longer in use, simplifying development. This process, while largely invisible to the developer, is constantly working in the background to maintain memory efficiency. Understanding its principles helps in writing code that cooperates with the GC for better performance. The new keyword explicitly allocates memory for objects on the heap, which is then managed by the GC. Every time you use new to create an instance of a class or an array, you are instructing the CLR to reserve space on the heap for that data. This is a direct interaction with heap memory allocation. Minimizing frequent heap allocations is crucial to avoid garbage collector spikes, which can cause noticeable performance hiccups in your applications. Each time the GC runs, it can pause your program briefly, leading to frame rate drops or unresponsiveness. Strategic memory management can significantly reduce these interruptions. Unity also leverages C# and the CLR, so the fundamental memory management principles remain consistent. This means that the concepts of stack and heap, value types and reference types, and the role of the garbage collector apply equally within the Unity environment. Your C# knowledge directly translates. However, Unity's real-time nature, especially in game development, makes efficient memory management even more critical for smooth gameplay. In games, even small performance hitches due to memory issues can severely impact the user experience. Therefore, a proactive approach to memory optimization is essential for Unity developers. Unity deals with both managed memory, handled by the CLR, and native memory, which is managed by Unity itself for assets like textures and audio. Understanding this distinction is vital, as native memory is not subject to the C# garbage collector and requires different management strategies. This dual memory system adds a layer of complexity. The Unity Profiler is an invaluable tool for monitoring memory usage and identifying performance bottlenecks. It provides detailed insights into how your game is using both managed and native memory, allowing you to pinpoint areas for optimization. Learning to effectively use the profiler is a key skill for any Unity developer. Common Unity-specific memory issues include frequent object creation and destruction, and used assets, and memory leaks from unreleased resources. These issues can quickly accumulate and degrade performance, especially in long-running game sessions. Recognizing and addressing these patterns is crucial for maintaining a healthy memory footprint. To optimize memory, minimize heap allocations by using object pooling for frequently created and destroyed game objects, like bullets or enemies. Instead of instantiating and destroying objects repeatedly, object pooling allows you to reuse a pre-allocated set of objects, drastically reducing GC overhead and improving performance. Prefer structs for small, lightweight data such as positions or colors, as they are value types stored on the stack. Using structs in appropriate scenarios can reduce heap allocations and improve cache locality, leading to faster access times and overall better performance for your game. This is a simple yet effective optimization. Avoid excessive string manipulation. Instead, use String Builder for dynamic string construction and cache strings when possible. String operations often create new string objects on the heap, leading to frequent allocations. String Builder modifies a single string object, and caching frequently used strings prevents redundant allocations. Always release resources by destroying objects when they are no longer needed using destroy and unload and used assets. Failing to properly destroy objects or unload assets can lead to memory leaks, where memory is held on to even after it's no longer required, eventually slowing down or crashing your application. Proactive resource management is key. Optimize your data structures by choosing appropriate collection types like arrays, lists, or dictionaries based on your specific needs. Each collection type has different performance characteristics regarding memory usage and access speed. Selecting the right one for the job can significantly impact your application's efficiency and memory footprint. Visual Studio offers powerful built-in memory profiling tools to help you analyze and optimize your C# applications. These tools provide a deep dive into your application's memory usage, allowing you to identify exactly where memory is being allocated and how it's being used. They are indispensable for serious performance tuning. You can take snapshots of memory at different points in time and compare them to identify memory leaks and large object allocations. This comparison feature is particularly useful for tracking down memory growth over time and understanding which objects are accumulating unnecessarily. It's a powerful diagnostic capability. Utilize Just My Code to focus the profiler on your project's memory usage, filtering out system and framework allocations. This feature helps you concentrate on the memory consumed by your own code, making it easier to pinpoint issues within your application rather than getting lost in the complexities of the underlying framework. It streamlines the debugging process. Understanding memory layout, the stack, and the heap is fundamental for both Visual Studio and Unity development. These core concepts underpin how your programs operate and directly influence their performance and stability. A solid grasp of these principles will empower you to write more efficient and reliable code. We encourage you to actively use profiling tools to analyze and optimize your projects, leading to more robust and performant applications. Regular profiling and optimization are not just for fixing problems, but for continuously improving the quality and efficiency of your software. Make it a regular part of your development workflow. For further learning, explore the official Unity documentation on memory management and C# memory resources. These resources provide in-depth information and advanced techniques that can help you further refine your memory optimization skills. Continuous learning is key to mastering memory management in game development and software engineering.